Welcome to iLecture Online, and here's a new topic for discussion called conservation of energy. And so what I'm going to show you here is a really interesting, straightforward, easy to apply method to solve a lot of energy problems in physics. And the concept is rather simple. What we can say is that, for example, we take a snapshot of an object that has potentially mass m, that will be in some position, maybe some height above the ground, with some initial velocity, and maybe some forces pushing it. So this is the initial state of the object, and then some time later, the object will be in a different state, and we'll call that the final state, where it will be perhaps at a different height, perhaps it will have a different velocity, and perhaps in the process of going from state 1 to state 2, or initial to final state, it had to overcome some friction or wind resistance. So how do you set up an equation to relate those initial and final states to each other? What you can always say is that energy is always conserved, and therefore we can say that energy initial must equal energy final. So what are the types of energies that this object can have? Well, it can have potential energy and it can have kinetic energy. So the initial energy that it has in this state right here means that it has some initial potential energy and some initial kinetic energy. So that would be the total energy the object can have. It's a sum of its potential and kinetic energy, and in the final state, when it has a different height above ground and a different velocity, it will have a final total energy or a final potential energy and kinetic energy. However, that's not the total picture, because we could also, while it's transitioning from initial to final position, it can also be subjected to a force. Somebody could be doing work on the object, and of course if you're doing work on the object, you're adding energy to it. So that means we can also have additional energy available because work was done on the system, so we have to add to that any potential work that was done on the system. So it will have not just the energy that it started with, but additional energy that was given to it in the process by the time it gets to the other side. So that means that it could have more potential energy or more kinetic energy or both, simply because work was put into the system and more energy was added. But then of course we sometimes have to overcome friction, which means that energy could be lost in overcoming friction. So some of the work that we put into it, or some of the potential kinetic energy the object had initially, could have been used to overcoming that friction. So we have to account for that friction on the other side of the equation. So we say plus energy lost due to overcoming friction, which means, if you think about it, if all the work that we put into it was used to overcome friction, and let's say that the amount was just enough, that means that the sum of the potential kinetic energy initially will not have changed. It will be the same as the sum it has over there. If the work we put into the system was greater than the energy lost, then these two will be greater than those two combined. And if the work put into the system was less than the energy lost over here, then of course more energy was lost, and that means that the total sum of these two would be less than the total sum of those two. And that's kind of the way to look at it. So this equation right here is the all-inclusive equation that will be able to solve just about any conservation of energy problem. And I'm going to show you a whole bunch of examples by using this equation. Now it turns out that we don't always have work put into the system. We don't always have energy lost. We may have zero potential energy initially if it starts off on the ground, or it may have zero potential energy when it ends on the ground, or maybe when it starts out it's not moving, or when it's finished it's not moving. So you can see that all those terms are available in the initial equation, but then when you look at the situation, you have to adapt it for things that are a little bit different. So anyway, that's your basic introduction to how to utilize this equation to solve energy problems now, or energy conservation problems. So now let's go look at these next videos coming up and see how we actually do so.